All right, welcome everyone on YouTube, everyone on Zoom. It is September 25th. Yeah, 2024. So we have our next Water, Wetlands, and Watershed seminar. And this week we are lucky enough to have Dr. Z Zhang with us. Let me make sure I can share your screen. Let's go ahead. Okay. All right. So Dr. Z Zhang is with us today. He's an associate professor in the Department of Computer and Information Sciences and Engineering at UF. And we also got to know Z through his participation in the Center for Coastal Solutions over the past 2 or so years. Dr. Zhang received his PhD in computer science from University of Minnesota in 2016 and his bachelor's in electrical engineering from University of Science and Technology in China in 2010. His research interests include data mining, machine learning, artificial intelligence, and he's been particularly looking at how to better predict flooding using remote sensing and machine learning. I guess not just flooding, but all sorts of natural disasters using machine learning and remote sensing. And he's been funded by numerous federal agencies, including NSF and NOAA, UCAR, and several industrial grants as well. So Z, the floor is yours. If people pop up, I might come up and just hide this multiple times.
Yeah.
You should be able to go, and I believe this clicker works.
Thank you.
Yeah.
Yeah, thanks, David, for the introduction. I'm really glad I have an opportunity to give a presentation in this seminar. Today, I will talk about my research on deep learning for spatial temporal data in scientific application, especially geoscience applications. And like David mentioned, my background is data mining, data science, AI. I develop tools that can potentially be useful for geoscience problems. And I hope today in my presentation, I can learn some good advice about what are the other use cases or interesting geoscience problems that can motivate new research in my group and for collaborations. So today I will start with an overview about my research area called geospatial AI. And then I will talk about 2 representative projects ongoing that address some of the challenges. And then I will briefly talk about future research. And geospatial AI, first, I want to talk about some background. Over the last decade, artificial intelligence has revolutionized the society through vision, language, applications, and computer games. And you might all heard about ChatGPT, for example, or AlphaGo. Those are great examples. And the wave of AI development was driven by the available big label data, big training data, and the advanced computational hardware like GPUs and smarter models and algorithms. And given the success of AI in language and vision domain, and people often ask questions, can AI also have the advanced science, especially like geoscience domains? And this was motivated by a number of grand societal challenges like national water resource management, agriculture, food security, and monitoring coastal hazards, and mitigation and adaptation to climate change. So we know geospatial AI is important. So what is GeoAI? This is the emerging area intersecting AI and the geospatial information science or geodomains. And there are different ways to tackle this domain. One angle could be apply existing off-the-shelf AI models from vision language community applied to geodomain problems. But I'm on a different angle. I'm interested in probing new AI methods to address unique challenges of geodomain problems. And here I want to show one example in flood mapping. This is the area imagery in Hurricane Matthew flood in 2016. We can see there's a flood areas. And flood mapping aims to identify the extent of flood water and maybe depth as well from the imagery. And this is result for the traditional machine learning using random forest, for example. It can really easily detect the exposed flood water, but there are a lot of flood water below the tree canopies or other obstacles. It's hard to identify. And we also tried using recent deep neural network, like UNet model. It still does not work well for those areas obscured by the tree canopies. In contrast, we developed a flood mapping algorithm that infuse how water flows on geographic terrains into the machine learning model or deep learning model, and we can identify more close flood extent. So this example shows that sometimes a need to customize AI algorithms and models to address the unique challenges in geodomains. And because of the significance of this topic, there are several emerging symposiums and workshops and many conferences like Oak Ridge and AAG and in data mining conferences and GIS conferences. And some of these are a little outdated. There are more recent years versions. And so what are the unique challenges of GeoAI, AI in geodomains? There are several basic challenges. First, about the spatial temporal data, it has the autocorrelation effect, heterogeneities, and there are also multiple spatial temporal and spectral resolutions of the data, and diverse noise, missing data, and gaps. And more importantly, spatial temporal problem often comes with domain physics and constraints, like the terrains in topography in many hydrological applications. It's important to integrate or infuse some domain physics and constraint into the data-driven neural network or machine learning models to avoid the spurious patterns or make it more robust. And last but not least is the positive ground truth. In geoscience problem, very often collecting ground truth is both slow and tedious and expensive. It involves sending a field crew. So this is not scalable. Sometimes we have to solve the problem training neural networks with little or few labeled data. So because of these important challenges, AI for deep learning for spatial temporal data has been listed as one of the open research questions by a government report. So my research aims to address some of these challenges in the context of real-world scientific applications. Here, I want to highlight a few representative works, like to address the challenge of missing physics in machine learning models. I designed terrain-aware spatial machine learning or deep learning models for flood mapping applications, like the example I showed earlier. And this was collaborated with USGS and the NOAA National Water Center, funded by NSF, some agencies. And to address the challenge of incorporating the complicated spatial and temporal dependency, like long-range multi-scale dependency structure, I designed unique transformer models for irregular points or irregular unstructured mesh. And this was potentially useful for coastal monitoring or simulations. And we have some initial results. And this was collaborated with Dr. Matani and another colleague on HPC domain from William Mary. And to address positive ground truth, I work on weakly supervised deep learning. Weakly supervised means that we train the neural network from a weak label instead of well-refined labels from GIS expert. We may use some less accurate labels and start refine the label while training the deep neural network models. And this was developed in the context of national hydrographic dataset refinement applications in collaboration with the USGS. And it was funded by the machine learning program. And we have a new project to apply the tools or develop the tool further for coastal salt marsh wetland applications, monitoring the pond collapse in collaboration with Dr. Oboto here at Center. So today, because of limited time, I will talk a little bit about the first two problems. And I just want to give a little bit early note that some of the slides are a little bit technical, prepared for computer science audience. And I hope I can get some more advice about how better apply the tools to real problem in geoscience, and or if there's any new applications. And I will try to summarize the techniques in a little bit more intuitive manner. And feel free to stop me anytime if you have any questions. So I will have a talk about two representative works. One is the development of AI models for geosensor or simulations. Particularly, I want to focus on the sensor observations that spread in the continuous space and at irregular locations, or the simulation models that the cells are on an irregular or unstructured mesh. And if you look at the cell position, those are also irregular points. And this kind of problem is important in environmental monitoring, like coastal water quality monitoring or coastal circulation modeling, where the simulation data are on the unstructured mesh along the coast. And here is the problem definition. The input data is a set of massive number of point samples in a continuous space. Each one may have some explanatory features. Like in water quality monitoring, this may be the remote sensing spectrum registered at some point. And it also has a spatial location, and the Y is a target variable. It could be water quality variables. And given this model, given this problem data, we want to train a model so that we can predict the variable at the new locations or at the same location with the feature based on the features. And why this problem is challenging? The first challenge is the complex dependency structure. So given all the point sensor observations, there are long-range spatial dependency, not only within the nearest neighbors, but may also be along far away point sensors, like water quality may be governed by the ocean currents, and it has a longer spatial span. And this dependency may come from multiple spatial scales. And also the samples may come from non-uniform distribution. Some areas will have denser observations, some areas more sparse, and the prediction is relatively more uncertain. And the computational cost is also quite high because we need to model the dependency structure across point locations, a lot of sample pairs. And last I mentioned, there's an uncertainty in the predicted variable. For example, some sensor may have noise essentially, or some areas very sparse without much coverage of the observations. Those areas tend to have a high uncertainty in the prediction. We want the predictive model to aware this such kind of uncertainty in the output. So let's quickly look at what are the existing tools for spatial data, deep learning for spatial data. Most of them are actually come from the computer vision domain. It models the spatial data as a regular grid. And a lot of the imagery models can be used by Fourier operator or other like vision transformer and so on. And some are developed for graph data, called graph neural networks. And this model only capture the dependency of one location with the neighbors on the graph. So it does not capture the long-range interactions between the locations. So our model falls into the third category, where the point samples are in continuous space at irregular positions. And some existing methods focus on single-scale spatial dependency learning, and we are learning multiple spatial scale dependencies. And next, I want to talk a little bit about our model architecture. The overall idea is called the hierarchical spatial transformer. At first, I want to check how many of you in the room heard about the transformer before. I mean, not the mechanical transformer. Transformer in AI.
Yeah, I couldn't explain.
In
Yeah, but you heard about it.
Yeah.
Yeah. So this is a model as the backbone for a lot of the recent powerful AI technologies like ChatGPT or similar vision models in computer like object detection and so on. So the main idea is to consider data as a set of tokens. Like in natural language, you have sentences as a sequence of word token. And what transformer does is to learn the attention between pairs of tokens so that it can capture the structure, complicated structure, the dependent structure in a natural language. So in this problem, we have considered each sensor observation point as a token. And we want to learn the dependency structure, also called attention weight, between the tokens to learn the spatial dependency. So that's the main intuition here. And next, I want to show the flow chart of a model architecture. You don't have to check all the low-level details. So we start with a number of all the massive point observations. Each is a token. Because these are irregular points, their location is not like regular image grid cells, which make it difficult to apply the existing vision models from off-the-shelf AI communities. And so we have to we first create a hierarchical structure using a spatial hierarchical index called a core tree, for example. And it's basically recursively partition the points in continuous space into 4 cells recursively until each cell has a maximum number of points fall into it. Through this core tree structure, we can get a spatial hierarchy of the point samples in continuous space. And once we have the hierarchy, we can use neural network to learn what is called a representation at different spatial scales along the trees. So one thing we do is to do a pooling operation, basically aggregating the samples within the cells, and then aggregating smaller cells into bigger cells in the hierarchy. This helps us to learn the embedding at different spatial scales. Another part is to do the spatial attention, spatial cross-attention learning across different cells or points. So these are some high-level intuitions. Once we learn the embedding, we have a decoder. When we want to make inference at a new location, we put into this tree hierarchy to figure out what scale or what position it belongs to in this core tree. And then we do cross attention from this query point to other existing learned point and cell embeddings. And finally, we make a prediction from there. And the main challenge is how we can learn the attention weight between a large number of points. And for each point, we need to get n pairs, and we have n points, so it's pretty expensive. So we cannot directly apply the vanilla transformer model for language processing. Then the question will be, how can we make it more efficient? The intuition is that when we compute attention from one point O1 here to all the other points, some of the far away points, it's kind of when people are looking at things far away, you do not have to distinguish them very closely. So we can have a coarse representation for these far away points. The further away those points are, the coarser resolution approximation we can use. That is the main intuition behind the idea. So next, I want to show this a little bit with an example. If we have a point O1, if we want to compute the attention weight by the default method, we have to do O1 to O2 to O3, O4 until O11. There's the 11 queries in the attention weight calculation. But if we are creating a hierarchical structure, we can approximate those far away points. Like for example, O8 to O11 in a coarse cell. For query O1, we have a close neighbor with exact point, a little bit far away, O1, O3 coarser cell. Here, these 2 boxes in the tree. And when it's getting further away, upper level squares, O5 is here. And then a more upper level is the 3 bigger box here in the first row of the core tree. So we just need to compute attention in a fewer number of queries, smaller than before. So that makes the models more efficient. We tested on some simulated point samples. It can learn up to 1 million point locations on one A100 GPUs. And we use coastal water quality monitoring as a test case. Some preliminary tests for the model or tool. I think more work needs to be done to make it better for the specific applications. And these are some baseline methods we compare with in the AI community. And here are some results. So the last row is our model. The others are others. It's close, and some we have a better performance. And we also test the efficiency of the models at different number of points. Let's say here, if we just use the baseline transformer without the efficiency optimization, it can only learn up to 10,000 points, then it's get out of memory or out of computing. But our model still scale here to around 1 million. Still, the time cost not very large.
See, so mean square error and mean absolute error.
Yeah.
Okay. And so
Yeah.
the bold is showing the best model. So for different red tide turbidity,
Yes.
Darcy flow.
Yeah. So the right type of turbidity are the coastal water quality monitoring, and this Darcy flow is numerical simulation data, more like idealized simulations could potentially be used for some real world applications. Yeah.
Okay.
Yeah, and here we also test. I didn't show the details. Our model also predict the spatial uncertainty of the model forecasting. The main intuition is that we want to know when the model does not know. For example, sensors sometimes noise or some areas the sample are sparse, and the predicted observation, the predicted point locations water quality may be more uncertain. And we compare this against some existing methods, like a Gaussian process has been widely used in a geoscience domain to model spatial uncertainty. But this model is not a deep learning model. There are some deep learning versions for Gaussian process. And we have a metric here called the AVU. Basically, it's testing like we split the prediction into two camps. Actually, four scenarios. One dimension is whether the prediction is accurate or not accurate. We can have some bins. Another dimension is whether the model say this is a confident or certain or uncertain predictions. There's a certain uncertainty score. Putting these two dimensions together, we can count how many times or what is the ratio of the samples the model correctly predict and also certain or confident. Or those models predict wrong, but also say I'm uncertain. These are the good cases, and we want to see how much, what is the percentage of this kind of prediction uncertainty in the overall predictions. The higher, the better. And in this number, we see Gaussian process has a score 33%. Our model has 54%, a slightly better. And one small note is that these numbers are not absolute based on the threshold we choose, but this result generally shows that the method somehow get the spatial uncertainty being quantified in the prediction. So this is the first application. We develop a transformer, not the transformer used for natural language or images, but for the new type of spatial data format, irregular points or unstructured mesh. And potentially this can be used in environmental monitoring and also to develop an AI surrogate for simulations on irregular mesh. And my hope is to find more application scenarios where these tools can be further developed and customized to solve real-world geoscience problems. And so this is the first representative project. The next one, I want to walk through another topic that we fuse the physical knowledge into AI models for geoscience problems. And we use flood mapping as an illustrative application example. Flood mapping is very important for disaster management, but the key challenge here is there's a limited amount of high quality training labels when we map flood on satellite images or area photos, because labeling the flood extent, especially the boundary, is very challenging. So then our question is, can we train neural network on weak labels, coarse, noisy labels? Those may be more easily available from a product for like lower resolution satellite imagery, like MODIS product, or from non-expert labelers. And to address that, we want to make use of some existing geoscience and domain knowledge. The main question will be how we represent the knowledge so that we can infuse them into neural networks. And the way we tackle this problem is to use symbolic logic. So first, I want to talk a little bit about the data format. It's a raster grid, and it has several explanatory feature layers. Those are mostly spectral bands in the satellite or aerial photos. And we have a class layer. We want to predict those are flood and dry in the flood mapping applications. And next, I want to just talk a little bit about the concept in logic, formal logics. And there are some definitions that define a predicate as a relation among objects, like a flow relationship between two locations. Water can flow from A to B. That flow relationship is called predicate. And the atom is just a predicate applied to two variables, like a flow between two location variables. And a rule is like a logic expression connecting different predicates or atoms together with logic like connections. Like if flood SI is basically is a predicate asking if SI location is flood or not, true or false. And the flow SI/SJ means there's a potential flow path from location SI to SJ on the terrain. If this both happens and SI is flood, flow possible, then SJ should also be flood. That's a very simple intuition. And we use that, and we need to ground these rules onto the specific pixel locations on a specific area. That process is called grounding, which we replace the variable with specific pixels. And a spatial knowledge base is basically a set of such rules based on location variables. It may not only be this rule, there may be more complicated rules based on real world application that we hope we can learn from the domain expert. Now here is a problem definition. We are given a raster framework, like a satellite imagery with spectral features and the number of pixels. Very often we are looking at high resolution pixels. And we also have coarse labels, like shown on the right here. This looks small. This is not a 1 pixel. It may be a coarse pack of pixels. And our goal, and we also have a set of geographical rules. These are some crafted by my student who try to learn a little bit. And I think it can further be polished with a real GIS expert or hydrological expert. But basically, we have the input the imagery feature, coarse label, noisy label, and some logic rules. We are hoping that these logic rules can have this process while we infer the true label and also train a neural network through the process, all together in the same framework. So this is our problem. And next, about the challenges. First, the label is imperfect, and there's a spatial uncertainty because of the label noise and coarse resolution. And also, there are physical constraints that we need to incorporate or infuse into the neural network models. And there's also high computational cost, because if we are working on high resolution satellite images, then we may have millions of pixels. If we put each pixel as a constant object in the rule induction, we have a lot of grounded rules. It's very slow to compute. So we have to find a smarter idea to compute this efficiently. And I want to talk a little bit related work. This belongs to what is called the weakly supervised Earth imagery segmentation. There are some work, but they do not consider physical knowledge. And it will create some spurious predictions, like in this area is inconsistent with the terrains. This is a flood area. This is ground truth. Yellow means flood. Purple means dry. This is a prediction of existing work. There's a gap here, inconsistent with what terrain tell us. And there are some other works that fuse physical knowledge into machine learning. Like most of them work on simple constraints, but we are trying to have a framework that allow more complicated physical knowledge expressions using logic. But most of them are for non-spatial problems. We are particularly focused on spatial problems in the raster framework. So here is our approach. And this slide may be a little bit technical. I will not go to the specific math or logics, but mostly have some high-level intuitions. This is our framework. So we are given the first knowledge base on top, and then the Earth imagery feature on bottom. We have several models. The first model here, this pink box, is a neural network. it basically takes the imagery and predict the flood labels on the pixels. On top is a knowledge base, like those logic rules. It helps us to capture the relationship between different pixels labels, whether one pixel is flooded or not, how it's related with another pixel, whether it's flooded or not. So we have these logical constraints among the pixel labels. We also have neural network that can predict labels. We combine them together and start with observe the coarse label and infer the true label at the same time. So that's the overall idea. So there's one module, we capture what is the error distribution, capture relationship between observe the noisy label and coarse label to the true label, get their relationship model. And then we model the relationship between the features, imagery pixel spectrum with the label, considering the logical rule constraints. So we put these together in an iteration to finally infer this true label while train this neural network well. And this rule will help us through the process. And another way to think about the process is that we start with a coarse label and we can use the rule to refine the labels to do some inductions. And one challenge here is that the rules, if we grounded every high resolution pixel, we may have millions of constant or objects to infer. That will be conditionally feasible. And the strategy we use is to start with a coarse resolution. We use a multi-resolution approach. We start with a coarse resolution raster, and each cell, a coarse cell is one object, spatial object, and we infer their spatial logics and infer some of the labels together with uncertainty. And then if there are some patches here that are uncertain, we know we need to go to a higher resolution, then we zoom in to a higher resolution grid for those uncertain patches using the rule logic reasoning, until we are reaching to a highest resolution where all the pixels are more confident. So this rule inference process also has a spatial uncertainty in it. Intuitively, in the flood mapping application, we start coarse labels, and when we get to the flood boundary pixels or patches, those are tend to be high uncertain because in coarse resolution, those are mixed patches. So we have to use that uncertainty to guide higher resolution zoom in operation for this rule inference. So that is the main idea. We use a multi-resolution approach in the logic inference, and that makes it more efficient. And next, I want to show some results. These are some basically benchmark comparison, like precision recall FN score accuracy in the flood mapping class. These are just the rule of game in machine learning. And here are some results. We are given the weak labels that are noisy and coarse, and this is ground truth. We have it for evaluation, but it's hidden in the model training process. And the result of the inferred hidden label of existing method are shown here, and our method is shown in the back. We can see compare with the ground truth, our inferred label is better. And most because we do the logic inference in a more effective and efficient way through the multi-resolution induction. And here is one specific case, how we can use the logical rules to help the neural network infer true label locations during the training process. This is the ground truth, and no hidden from the training framework. And this is the first iteration, coarse labels. We can see the boundary patches are uncertain. And gradually it zoom in more higher resolution, more certain boundaries. So that's the intuition. And we are also interested to learn about additional knowledge constraints or other geoscience applications potentially that can use the tool. We also have some sensitivity analysis for different noise level. Our model basically more robust when the noise level is high, but baselines perform poorly. Yeah. So in this work, we develop a neuro-symbolic model for geoscience problem. We have some geo knowledge base that we can use to train neural network from coarse labels. And we evaluate this framework in a flood mapping application. And in the future, we plan to extend it to more applications and better domain knowledge, like in forestry or other domain, wetland ecology and so on. And last, I just want to quickly talk about other ongoing research. We are currently also working on AI surrogate for large-scale spatial temporal simulations. So the main idea is the simulation is very important, like coastal simulation, for example, important for hazard forecasting, storm surge, for example. But those models are very computationally expensive. And those are also, some of the models are also very hard to scale up, even if you have more CPU cores using the traditional HPC architecture, it may not scale up very well because the complicated dependency across the mesh. And one emerging idea is to train neural network model as a surrogate for the coastal simulations so that it can make the same prediction but much faster, leveraging the GPU architecture. And there are a lot of ongoing work and quite some success in the weather forecasting domains using AI models. And I'm currently working on develop AI for coastal simulations. And we are currently testing vision transformer models, and we are going to explore more recent models like diffusion models. Those can capture potentially the uncertainty or probabilistic nature of the forecasting problem. We are also interested in fusing physical knowledge into the surrogate model so that the model prediction somehow is consistent with the physical laws to make the result more useful. And this is in collaboration with Dr. Matani Olabrada at the Center for Coastal Solutions. We have a new project coming up funded by the National Science Foundation, the OAC program. Yeah, so that's what I have today. And these are our sponsors. And any questions?
Give Dr. John a round of applause. I'll start with questions from the room and then we'll see if we have any from YouTube. I know a lot of that is new for folks here, but
yes,
please go ahead.
So when you were checking the ground truth against your model, I was curious, sorry for that second project.
Yeah.
What was the data you were putting into the model and letting it see? Was it just elevations?
you mean the input?
Mm-hmm.
Yeah, for the deep neural network, it's mostly the imagery spectrums. We are using high resolution imagery, so it's RGB, red, green, blue band, and maybe also infrared could be used. And in the rules, some of the rules, very importantly, we derived from the terrain structure, like the flow path. That is one crucial rule that we use. But we did not put the terrain into the feature. We could have put terrain into the neural network as well. Yeah.
But I think so you had hidden the true state from the model, but
Yeah.
I guess the question is, so how was the labeled true state used in the training?
Well, no, I think I got it now. You
Okay.
plugged in the vision and then you
Yeah.
checked how well it matched with the elevation data at the end.
Yeah, that's kind of the main intuition for this use case.
Gotcha.
Yeah, why it works. Yeah. The ground truth is more like more carefully labeled by hand. Yeah.
So for some of these that, talking about scaling up or down, basically kind of like resampling in a sense, like
Yeah.
from very fine to more coarse resolution. Then the model still takes a lot of power to like develop and train, calibrate, validate. If you're looking to predict forward, is it fast enough to give you like next day predictions or things like that?
Yeah, do you mean the first or second one?
I guess either
Yeah.
one, yeah.
That's a good question, yeah. I think there may be some potential to use the tool for forecasting context where there's uncertainty need to be considered or calibration with the observation to be considered. So far, I think the tool has not been set up to be able to do those kind of things. I think, yeah, there are some potential in the future to maybe extend the method to have a more multi-scale or multi-resolution forecasting and consider data assimilation kind of thing at the same time or calibration. Yeah, that would be more interesting and sophisticated use case, I guess. Yeah.
Yeah, and then you have to make sure that you have the forecast for the features that are important to the.
Yeah.
You need a forecast for the things that go into the model, you're gonna forecast something else.
Yeah.
Right? How about there on Zoom? I see Venetius and Brittany and Anmal and Mahima. Any questions from
I have a
Zoom?
question.
Yeah, go ahead,
This
AJ.
is just because my knowledge of like modeling is like very
Yeah.
general. What is like the difference between a quad tree and a classification tree, the one that you like give to a random forest model?
Yeah.
Just because when I was looking at it, it was on page 18, I was like, this is like conceptually, I guess, similar.
Looks like a.
Yeah,
a
yeah, it's
classification tree, but like
you're right.
you're not predicting something in a quad tree. So then what's the,
Yeah, let me go to the three example slides.
it was 18, page
Yeah.
18.
You can get to the slides.
You can escape if you want out, or you can just go back. Yeah,
Usually,
it's usually fine.
Yeah, this one is
Yeah.
mine too.
Yeah,
that's a very good question. So first, they are similar in the sense they are both tree structures.
Yeah,
And but the contents of the tree is different. In the machine learning domain, like a classification or regression tree, or also called decision tree, each node basically you are make a prediction on one sample instance.
right.
The root node and the internal node basically ask questions about the feature. For example, in land cover mapping application or flood mapping, if you are using a classification tree, you will need to you use it to predict whether a pixel is flat or not. And the question you ask in the tree node maybe how much greenness, how much redness,
Right.
yeah, how much maybe even the combined index, like a DVI index. And then after you, based on the questions from different answers from different questions, you get to a leaf node where prediction is made.
Right.
That's predicting the label for that sample. But for this spatial core tree, this is not a machine learning model to make predictions. Instead, this just have a hierarchical structure of point samples in a continuous domain. What it means is that it partitions the points in the space recursively into 4 cores. And consider each core as a tree node. So basically, this core tree, each root node, the root node is a bigger square.
Right.
And the first row is the 4 squares in the lower level. You see here, there are 4 squares.
Yeah.
Yeah, these are the first level, R1 to R4. And then each square may be further partitioned into 4 subsquares. And here I only show 2 subsquares and this square because the other are empty here.
right.
Yeah, so basically this is spatial hierarchy tree.
Okay.
Yeah.
So is this sort of like a Monte Carlo method but with nonlinear relationships among the variables?
Let me see. You're asking about the machine learning model here
Yeah.
that we built on top of the tree,
Yeah,
Monte Carlo. So you are asking about Monte Carlo
I
with,
mean, using the amount of error in a particular variable
Mm.
and then running it many times to see what's coming.
yeah, that's a great question. I have not, this is not using Monte Carlo simulations. But I'm curious that there may be some simulation problem that involves the sampling method you mentioned.
Mhm.
And can we use this hierarchical structure and the machine learning model architecture to incorporate those? That may be interesting, but so far I have not
What's more
considered.
not linear then?
Yeah, the nonlinear comes from this neural network
Yeah.
architecture. The neural network learn attention, and there's also the nonlinear activations. Yeah, so that it can capture the interactions, the complex interactions, nonlinear relationships. Yeah,
So one thing Enrique is working a lot on these spatial transformers or transformer models in general, and they seem like very data hungry.
yeah,
So we get a comment a lot of times, like
Yeah.
maybe the performance is better by R squared goes up by 0.2 or 0.05,
Mm.
but you need like 9 years of daily data instead of 3 years. And so
Yeah.
it's like a real trade-off. And especially like in the vision, like
Yeah.
2-dimensional, like map by time,
Yeah.
right? Like gridded water quality data. How much do you need in order to do a good job, especially for forecasting?
that's a very good question. Yeah. I guess in this paper, when we publish paper, the data sample we use, the real water quality sample is actually not very large. So that's really not really showing the potential power for transformer architecture. We just use this as a test case. But when it's come to the coastal simulation models, for example, that data is very large. And
Oh, because the simulations have data for every grid
yeah,
point.
every grid
Yeah.
point. in each snapshot, we get around 6 million cells, 3D. And originally it was every half an hour. So if we have 10 years data, that's tens of terabytes. That's one challenge we are facing now. And yeah. So come back to your question, I don't have a rule of thumb for the vision problem, but for the language domain, I think they can be somehow compared. For language domain, the more powerful foundation model like ChatGPT, more recent versions, it uses trillions of tokens.
Yeah.
And for vision domain, you can imagine each token as a small imagery block, maybe 20 pixel by 20 pixel, just for example. Then you can imagine how many of the things we need. Yeah. So it can be pretty data hungry. Yeah. So far, we have not tested really large scale training. And we just started a little bit testing for coastal simulation data and get some interesting results. We're hoping to get more results and publish it. Yeah.
Yeah, I think about like Lake Okeechobee has the cyan, like the remotely sensed chlorophyll. And it's, Sentinel-3, so a couple years, 5-6 years of data, maybe daily, but a lot of clouds. And so like the idea would be to be able to predict tomorrow or next day based on this sort of transformer, like visual neural network.
Yeah.
But if that is that enough data? Is that enough data?
That
to-
may be good to start. It's a daily, right?
Daily, so let's say you have like 2,500 images, or maybe
Yeah.
2,000 images or something
Yeah.
like that.
I think that should be enough to train a model. We just want to control the size of the model. Yeah, we'll need to like make the size of model relatively consistent with the training data amount.
Mhm.
Yeah, I think it should be trainable for vision transformer.
And maybe you
Yeah.
course in the
Yeah.
resolution, I don't know, and
Yeah, and another way is that there are already some pre-trained transformer model for satellite images. If it's from the same sensor, then we can use some of the pre-trained model. It's based on self-supervised learning without label for a lot of different scenes, and then fine-tune it on this particular application. Yeah.
it'd be fun to talk more.
Yeah.
Okay,
That's
all
good.
right, so we got no questions from YouTube, no questions from Zoom. I'll give you a pass this time because it's a hurricane, I guess, but we'll see everyone next week. So next week, I would like everyone to be sure, especially if you're enrolled in the on-campus section, you need to be here. We have a speaker coming from out of town, Dr. Royal Gardner, JD, and he's written a lot about the protection of wetlands based on recent Supreme Court changes. Other than that, we'll see you next time. Everyone stay safe, and thank you, Dr. Zhang.
Thank you.